It's time for our next data structure, hash tables. Hash tables, or hash maps, maps, unordered maps, dictionaries, objects, there are many ways to call this data structure. And different languages have different names for it and slight variations on the hash tables. Objects, for example, in JavaScript, are a type of hash table. The reason I'm starting the course with arrays and objects, or hash tables, is because these two are the most common interview questions. You're going to use them in any coding question. Me personally, I have yet to be part of an interview that you didn't have to know these. They are an absolute must. Now, luckily for us, pretty much every language has a built-in hash table, just like arrays. In Python, they're called dictionaries. JavaScript, as we said, are objects. Java has maps, and Ruby has hashes. And hash tables are very important all across computer science. You see them a lot in databases, in caches, and they're extremely useful. So what are they? And also, you may be wondering, what does the name hash table mean? Where did this name come from? Well, let's look at an example. Imagine you're going grocery shopping, and you have an object here, basket, and you want to add grapes as the property of the basket object. Again, we're using JavaScript syntax, but this should look familiar to you. So we want to set that basket.grapes is going to equal 10,000. We're buying 10,000 grapes because you can never have too many grapes. Now, first off, thinking about how we would store this with arrays, it would be a little bit more difficult, right? In an array, we have an index that's numbered and a value. With a hash table or an object, we get to set a key, which is grapes, and a value. So we get to set a key-value pair. So right away, we see some benefits in here. Now, a way a hash table works is we have the key, which is grapes. And this key is used as the index of where to find the value in memory. Remember, with arrays, we had the index, which was a number. But with hash tables, we use grapes as a way to find it in our memory shelf. This is done this way, with something called a hash function. But for now, we'll just assume this is a black box. We don't know what's going on here. All that's going to happen is we're going to pass grapes into this black box. This black box is going to do some magic, and out of it comes a key into an index where we want to store this value. So now our 1,000 grapes can be stored in this memory address, 711. And technically, it actually stores both grapes, the key, and the value of 10,000. Here, I've just simplified it to 10,000, just so it's a little bit cleaner. But keep in mind that it's going to store both key and value, and I'll show you a diagram showing this later on. So this black box over here gets to decide where to put the data on our memory in our computers. But you might be wondering, what is this thing? And why does it get to decide where to put all this information? For that, I'll see you in the next video. Bye-bye. What is a hash function? It's something that's used all across computer science. A hash function is simply a function that generates a value of fixed length for each input that it gets. All right, what does that mean? Well, I have here a MD5 hash generator. MD5 is the type of hash function, and there's many, many types. You might have heard of SHA-1, SHA-256, and many others. Using this hash function, let's see what happens if I do hello. You see that right away, MD5 hashes this string and turns it into this gibberish. That's what a hash function does. We give it an input, and the function generates some random pattern. Now, there's some key aspects of hash functions. First is that it's one way, in the sense that if I give somebody this, they have no idea what the input was. And it's practically impossible for me to have any clue as to what the input is. The second is that no matter how many times I put hello in there, it's going to be the same. But as soon as I change one thing, it's going to completely change the output. If I go back to hello and Watch me just change to capital H, even a capital letter. So it starts with 5D4. If I do capital H, it's completely different again. And looking at this, we can at least say that, I don't know what this is useful for, but the one thing that I know is that no matter what, if I give it the same input, it's going to give me the same result, but I have no idea how to convert this back into hello. This is what we call idempotent or idempotent. There's different pronunciations. I'm not really sure which one's which, but it is a fancy way of saying that a function, given an input, always outputs the same output. Now, the one benefit and why we would want to use this in a data structure is that we get really fast data access. Because all I have to do to find grapes, or basket.grapes, is to pass grapes into something like an MD5 hash. It generates this number for me, and I immediately know where it is in my memory on our computer. But this doesn't look like an address, does it? Technically, a hash function that we use for hash tables is going to take grapes, generate some sort of gibberish, and then convert it to an index space, or an address space that it has based on this number. You see, unlike arrays where we just had ordered indexes, with hash tables, all we need to do is give it a key and we know exactly where that item is in our memory. But you might be wondering, this black box hash function, doesn't it slow things down? Because every time we want to add a property and a value, grapes and 10,000, to a hash table, we have to run it through the hash function so we can decide where to put it in memory. And if you've noticed that, good job. That is a big factor. You don't want this to take a very long time because, well, every time you add a property to memory or retrieve a property to memory, because again, both times we're sending the key grapes into the hash function to find where to get it from. We need this to be really, really fast. And underneath the hood, remember, because hash tables exist in all languages, they're implemented with an optimum hashing function that's really, really fast. As a side note, hash functions like SHA-256 take a really long time to generate a hash. And it is an overly complex hashing function that is used a lot in places like cryptography, where you want this to take longer, but that is outside the scope of this course. If you're interested, I do recommend that you check out the differences between these two. To review, we have a key that is grapes. We send it through a hash function that is going to hash something really, really fast and then map whatever the hash came out to be into a memory address where we want to store our data, our grapes 10,000. And when it comes to hashing functions, you typically leave this to whatever framework or language you're using. And we usually assume a time complexity or big O notation of O1 because this happens really fast. All right, now that we understand what this black box does, let's talk a little bit more about hash tables, why they're useful, and why, in some cases, are better than arrays. Looking at hash functions, we can start to think about what actions they perform and how fast it can be done. When it comes to inserting something in our memory space, well, it's going to be O of 1. We hash the key, such as grapes, through the hash function and places it automatically into the address space that it comes up with. Lookup is the exact same. We access the property. That property is going to get hashed and direct us exactly to the address to find the values. What about deletes? Same thing. We simply use the key. Right away, we know where to delete the item from. And because it isn't ordered, we don't have to shift indexes like we did with arrays. Everything is just nice and simple. What about searching? If we want to find something in our basket, like apples, well, that's easy too. We simply use hash functions. If we go to our playground, in JavaScript, I can create an object, let's say let user, and this user will have property of age 54. Let's say that the name is going to be Kylie. Magic, well, let's say Kylie does have magic skills, so we'll set it to true. And for fun, let's say that the scream is a function that will just console.log a scream. That was not the strongest of screams, but I don't want to scare people around me. When I run this, I've created a user object, and the age, 54, name, Kylie, magic true, scream, and this function are all going to get placed somewhere in memory at different addresses. But I can access this really, really fast. I can say user.age, which is going to give me 54 at 01 time. Perhaps adding a new property, I can just simply say user.spell is going to equal abracadabra. And if I run this, and let's just check out what the user object gives us, we see that we now have the spell abracadabra added. This again is access of O1 is O of 1 because we take it through the hash functions and the computer decides where to put both spell and abracadabra in memory. And if I run user.scream, same thing. Oh, I cannot spell scream. Same thing. I get to access this function in memory really, really fast at O of 1. How amazing is that? And I know what you're thinking. Hash tables are amazing. We should be using them all the time. And you're right, we should be using them in a lot of cases. But as we know, there's always pros and cons. Now, let me talk to you about one of the main problems with hash tables. And I have a nice visual to demonstrate this for you. I'll link to this in this video so you can play around with it later. I have a little animation here where we have 12 memory spaces. Remember, our computer has limited space. And when we create an object or a hash table, the computer decides how much space to allocate. It's not going to allocate all the space to the hash table. It's going to allocate a bit of it. And I'll show you later on when we implement our own hash table how we can adjust the size. But seeing that there's only 12 spaces, you can imagine if I insert here, let's say 1. Let's see if I can make this bigger so you can see it. Yeah, there you go. I'm going to insert, let's say the number 3 gets inserted here. Let's do 55. Insert it. Ooh, what happened there? Did you see that? The hash function randomly assigned a space in memory and put it in 3. Uh-oh. Remember, there's nothing telling the hash function to evenly distribute until everything is full. Although hash functions are optimized to try to distribute this data all over, it also matters what we put into it. So when 55 gets hashed, well, this hash function generates the address location of 3 to put it in. And because we already have 3 there, it does something funny here. Let's keep adding here and see what happens. I'll add 2, maybe add 12, and finally add 14. Uh-oh, it did the same thing again. And what we just noticed here is something called collision. And a collision looks something like this. We have the keys. Let's say we're inserting the name and the phone number of a user. And we initially place John Smith. This key gets hashed, gets placed in the address space of 152, and gets stored. Remember how I said it actually stores both keys and values? It stores in something called buckets, John Smith, with the value, that is its phone number, right here. And then we keep going with Lisa Smith, then Sam Doe, then Sandra. Oh no, as soon as we hash Sandra D, it becomes the same address space as John Smith. And we have a collision. And because of this collision, we need a way to store both users somehow in this address space. And something funky is going on here with this little circle and then a point and Sandra D. And just a hint here, this is actually a new data structure that we're going to learn about called linked lists coming up. You see, with hash tables, we can't avoid these collisions. With enough data, with limited memory, we're always going to have this collision. So there is a possibility, if we go back to our example, and I refresh here to start from scratch, that we constantly just add, despite our hash table that's really, really fast, constantly just keep adding to the same memory space, which slows down our ability to access or insert information, because now if I want to check what's in this address space, I have to go 1, 2, 3, 4, 5, and so on and so forth. Theoretically, when you have a collision, it slows down reading and writing with a hash table with O(n) divided by K, where K is the size of your hash table. And remember, because we remove constants and simplify things, it becomes an O(n) operation. Now, collision will likely happen in any hash table implementation. And luckily for you, you're never going to have to really implement it yourself. And it's not a very common interview question, but you do want to know about it so you can talk about it. There's 2 common ways to deal with these collisions. I showed you one of them with something called linked list, which we'll talk about later on. But if we go to the hash table Wikipedia page and look at collision resolution, you can see that there's a ton of different ways to solve collisions. The way that I showed you is called separate chaining, but there's different methods like open addressing and Robinhood hashing that you can read about if you're really interested in the topic. The point I wanted to make is that there is a bit of a downside. When we talk about fast lookups in hash tables, occasionally, depending on the hash function, it might take O(n). All right, let's keep going and expand our knowledge of hash tables in the next video. Welcome back. Now, hash tables are implemented differently in different languages, but most of the time, the key and the value can be any type of data structure. We saw here that we can have a function as a value. We can have another object if we want as a value. We can have an array as a value if we want. And I mean, you can do this in arrays as well. We don't just have numbers and strings in arrays. We can have arrays of objects. But you can also sometimes have keys that are more than just strings. You could potentially have functions as keys and a value that is also a function, or perhaps a number or an array, whatever you want. Now, in JavaScript, in an object like this, if you pass a key that is a number or a function, it actually gets stringified and it only allows string keys. But with the new version of JavaScript and ES6, you actually have something called map and sets, which also may be familiar in other languages. A map is created like this, and the difference between a map and an object is the fact that a map allows you to save any data type as the key. Remember, with an object, you can only save the key as a string. With a map, it allows us, if we want, to even have functions as keys or arrays as keys. And another benefit of map is that it maintains insertion order. What does that mean? Well, with an object, there is no order, is there? If we go back to our diagram, our data is inserted randomly in different places. If we go back to our user's example, we see that there is definitely no order. When we grab all the values of an object, we start with, let's say, Lisa Smith, which was entered second, then John Smith, then perhaps Sandra D. Sam Doe gets selected last. There is no order like there was with arrays. But there are some versions of hash tables, like maps in JavaScript, that maintains this order of insertion, so that when we loop through items in an object, we have this maintained order. Sets is another feature, very similar to map. The only difference is that it only stores the keys, no values. So you see here, each language, as we mentioned, comes with its own pre-built versions of data structures. But at the end of the day, all of them are hash tables. But in order to truly understand how hash tables work, I think we should build one. In the next video, we're going to do just that. Welcome back. It's time for us to implement our own hash table. But let's do a bit of an exercise. And this may be difficult, so don't get upset if you are not able to finish it. After this, I'll provide a solution video and we'll walk through it. But as an extra challenge, I have created a template for you. A new hash table that we're going to create. Yes, I know JavaScript already has objects, and we can just simply create one like we've seen before, but what's the fun in that? Let's create our own. Now, this hash table has a constructor that will receive a size. So when we create this hash table, we're going to give it a memory space size of 50. Let's say that we only want 50 shelves of memory. We're going to create this .data where our data will live. And within it, it's going to create a new array. And this array is going to hold our information for us. So we would have something like grapes and 10,000 as our bucket. So the first item in the array will be an array that is grapes 10,000. Remember, if we looked at the diagram, we have these buckets that our data lives in. And because right now we're implementing our own hash tables, we're using array instead of objects. But the idea is that using a new method that you'll have to create, which will be called set, you're going to be able to set grapes as the first index in the array and the number of grapes as the second index in the array. And from there, we can have another method, get, which retrieves the grapes and returns 10,000. Now, you're probably wondering, oh boy, what is this gibberish? And I wrote this ahead of time for you because it's not really important as part of the course. But remember, we need a hash function in order to create a hash table. And I've created here the smallest, tiniest hash function you can think of. We're going to talk about what this actually does in the solution video. For now, all you have to know is that it's going to just generate a hash for us. For example, if I do underscore hash here and give it a key, so let's say that I want to insert grapes, and I click run, I get 23. If I click run again, I always get 23. If I change grapes to 2 S's, I get a different memory space. If I just type in randomly here, again, I get different memory spaces, all from 0 to 50. So your challenge here is to create these two new methods, set and get, that adds to this .data and retrieves from this .data. Again, if you're not super familiar with JavaScript, this may be hard, but give it a try. And in the next video, we'll walk through step by step. I'll see you in that one. Bye-bye. Welcome back. It's time to walk through our own implementation of hash table. Now, before we get started, I do want to mention something that you may be wondering about. That is this underscore over here. What does that mean? In most other languages, like Java, when you create a class, you can have private properties. That is, properties that I can't access outside of this class. So I wouldn't be able to do my hash table underscore hash and access this property or method. Now, with JavaScript ES6, that's not really possible. And there is a common standard, which is to put underscore here in the JavaScript world, which says this is a private property. Now, this is just meaningless, really. I can still access the hash method, but it is a developer standard in the JavaScript community to let other developers know that, hey, you shouldn't be accessing this, even though you technically can. And there are ways to make it work and have private properties, but it requires things like closures, symbols, or weak maps, which, again, is beyond the scope of this course, and we don't need to worry about. So that's where the underscore is coming from. We're not usually going to access hash function like this. All right, now that we got that out of the way, let's talk a little bit about what this does. If I enter in here grapes, we first create a new variable that is hash, that is equal to 0. And then this key, we're going to grab the length of grapes. So that is 1, 2, 3, 4, 5, 6. And we're going to add 0, which comes from the hash, plus key character code at. And character code at in JavaScript simply gives us an integer between 0 and this number, representing the UTF-16 code. So that's just an encoding. It's pretty much saying, give me a character code, because remember, in memory, a string or a letter is represented as a number. So this method allows us to say at index whatever we put in the parameter. So let's say we're looking at index of I, the very first one will be G. We're going to get the character code for G, that is a number. We multiply that by the index again, just to make sure it makes it unique. And then we use what's called the modulo operator to make sure that this stays within the length of 50, the size of our data. And then we return the hash. An easy way to see what's happening here is to simply console.log hash. If I run this, we see that it's going to loop through our grapes, character by character. It's going to generate some sort of a hash. And because this hash gets constantly looped over, we include whatever the generated, let's see, the first one is 0. It's going to say 0 plus whatever this is. Then the next iteration, hash is going to equal 14 and generate something else, which is 8, and keeps going until we get 23. You can take your time and go through this code if you really want to. Again, this is not the focus of this video, so let's move on. Using our hash function, let's do our very first method. Let's create the set method. This set method is going to receive a key and a value. And just so we can see this and what's going to happen, we'll run this method here saying we want grapes to equal 10,000. Lots of grapes because they are delicious. If I run this, I get undefined because, well, this isn't really doing anything. The first thing we want to do is to create a variable called let address, which will represent where we want to store this information. And we'll say this dot hash key. So all we're saying is store this data that we're going to insert, the key and value, in this address space that is created by our hash function. And we give it the key of grapes. Remember our little animation. We're sending the grapes into that magic little blocks. That is the hash function. From there, we simply say if this dot data address, if it doesn't exist and there's nothing there, because remember, in a hash table, we can have collisions. And because we only have 50 spaces, 50 shelves here, we might have these collisions with enough data. So we're going to check if there is nothing there. In that case, well, just simply add that data. We're going to say this dot data address is going to be an array. And in this new space, new address space, we're simply going to add by doing push key value. So let's run this and see what happens. Oh, and I have a misspelled address here. Let's run that again. I get undefined. But let's see what happens if I just console.log this dot data here. Whoa, check that out. We have 23 empty items. On the 24th item, we have grapes, 10,000, an array here, and then 26 empty items after that. Remember, we have 50 shelves in our memory, and we have 23, 24, plus 26, that's 50. Except our grapes was inserted somewhere in 50, it looks like the 24 spot. Very cool. But what happens if this already exists? If I change the hash table to just have, let's say, 2 memory spaces, and I click run here, I get 1 empty and grapes. And if I change this around, do you see that? If I click again, and let's say go back to just grapes, check out what happens to my hash table. I click run, and it just deleted my previous entry. We have a collision, but we're not doing anything about it, and we've just deleted our data. That could have been really important user data. We definitely don't want that. So in order to solve that, we simply say if, because we're checking here if there is nothing in that address space, do this. Otherwise, simply add on to that array. So we can actually just run the same command here. A nicer and cleaner way of doing this is to actually just take out the else, because regardless, we're always going to be pushing key and value. We're always going to be adding the key and value that we add to the data. So all we do is just remove this, so that when I run this, and just so we know what's happening, let's return this .data here. I'm going to hit run. And if we add here, let's say another item, this time we'll say apples and just 54 apples. If I run this, did you see what happened here? If you look closely, we have one empty item and then an array that contains inside of it the first index that is an array and a second index that is another array, because we've just pushed onto our existing array because our memory space is only 2. Very cool. That wasn't too bad. Let's keep going. The next one is, well, I want to be able to grab grapes and apples. We can use the get method here, which will receive a key. And this get method is going to work very nicely by just saying get and then what we want to grab, which will be grapes. We're going to do the exact same thing in that we run it through that black box where we're going to use the hash function to get the address of where we want to go. And now we have the address to where we want to grab our information from. However, remember that we store this information in a bucket. So we have grapes and 10,000. How do we grab that? We know where to get it from now. We have the address, but we now need to loop over and grab grapes and then 10,000, or apples and then 54. Let me show you what I mean. We'll first create a variable saying current bucket. That will just be this.data or address, just so we don't repeat ourselves and we have a reference to this address or to the address and the data value. So this means if we console.log current bucket and I run this, you see that I have the current bucket, even though this has 2 items. Remember that it is technically just within its own bucket, within one array. If we increase this memory space to, let's say, 50, we see that this bucket contains grapes. So we're grabbing this information, but all we want to do is have 10,000 being returned. That's how hash tables work, or the get in the hash function works. Well, all we need to do is to say if current bucket, and we'll say .length. That is, if this current bucket has something in it, in that case, we are going to do something. Otherwise, we're going to just return undefined because there's nothing in the bucket. We're checking if this actually exists. So if there's nothing in the array, if the length is 0 and the array is empty, well then, we're not interested in it. As a matter of fact, we actually don't even need the length here because remember, initially, it's just going to be an empty array with undefined, and we add an array to each slot whenever we set something, and it's an empty address. So we can just leave it like that because if it's undefined, it'll skip over and return undefined. Now in here, we will do a for loop because remember, we might have multiple items in this bucket, like we saw when we had 2 memory spaces. In which case, let me actually demonstrate that. So we can see it. Say run, and current bucket. I can't spell, let's run that again. All right. If we console.log current bucket and run this, we see that we have 2 items in that bucket. So we will need to loop over using our favorite for loop, which we've done a ton by now. We're going to say, as long as I is less than the current bucket.length, just increment I. And within here, this is a little bit tricky, so hopefully you follow. I'm going to say if current bucket I, which is the index. So remember, it's going to say 0, which is going to grab this, then 1, which is going to grab this. If current bucket, the grapes, so if I do 0 here, that means grab the first, in our case, the I, so it's going to be 0 first, grab this first array, then grab the 0 index within this array, which will be grapes. And then once it loops the next time around and I is 1, it's going to be apples. Check that against the key. Remember the key that we receive here that we are looking for. So if grapes, which is the key, matches with this item, in that case, just return the current bucket, the I, and 1, because we want to return 10,000. Hopefully you follow here, because if I run this, I get 10,000. The get grapes is 10,000. If I do apples here, it is 54. How cool is that? And looking at this, I hope you understand on a deeper level the time complexity implications of hash tables. Even though we're doing a loop here within the hash function, remember that hash functions are really, really fast. We're just looping over the key, so we don't consider this to be O of n. This is very, very fast. It's O of 1. When we set something, there's no loops here. We're just adding it to our data. We're just pushing it. So that is O of 1. And if we go to get, most of the time, if there's no collisions, it's going to be O of 1. And in real life, most of the time, you can consider that it is O of 1. But in our really bad example with just 2 memory spaces and not a very good hash function, well, this can become O of n. But for now, because we're good programmers, that won't happen, right? Everything will be good. We have O of 1 get. We have the for loop here that might create that list we saw in our example. See this list that we have here? This is what we created. And it would be O of n if this list just kept growing and kept growing and kept growing. But there is one other method that I want us to build and to showcase to you one other downside of hash tables. What if we wanted to go through all the keys of the hash table? How would we do that? We're going to try and implement that in the next video. Bye-bye. Welcome back. Let's implement one last feature in our hash table over here. I want to create something called keys. And keys allows us to iterate or loop through all the keys of our hash table. In this case, grapes and apples. And let's add a few more just for fun so we see what's going on. We'll add oranges, and we don't like them too much, so we're only going to add 2 of them. Now, if we run keys, ideally, it's going to iterate and spit out grapes, apples, and oranges for us to see what we need to go shopping for. How would we go about building this? Well, because we're going to do some sort of looping, I'm going to start off by creating a constant. Let's call it keys array. And this is going to be an empty array. Within here, we're going to loop. So for let I equals 0. And as long as I is going to be less than this.data.length, we're going to increment I. In here, we're saying we want to loop through all 50 item spaces. All the shelves, one by one, we're going to loop through them. Yep, that's a lot of iterations. And if in the shelf there is some sort of data, if it's not undefined, completely empty, and there is something valuable for us that we want to look, because remember, we allocate 50 spaces on the shelf, but we've only placed 3 items or 3 data points on that. So if there is something in that memory space, in that case, we can just say keysArray.push this.data, and we grab the index, so the first array or the array that we're at right here, and then we want to grab apples, right? Well, if I do 0 here and now hit run, well, we have to return something. Let's return here the keys array at the end of all of this. So after all the loops, we're going to simply say return keys array. If I run this, I get grapes, apples, and oranges. That's fantastic, but I just wanted grapes, apples, and oranges. To see what's going on here, let's console.log this.data I, which is what we're doing here, what we're pushing. And if I run this, we see that we get arrays within the array. Because remember, we have one massive array, and each time we create a new shelf space, we have to have a new array that we create and we push into that. So a little bit of a gotcha here. We have to say 0, which removes the outer array, and now another 0 to grab the first index of this array. Just like that. So if we add another 0 in there to access the first index of the array, we click run, look at that. We get grapes, apples, and oranges. Well done. We've just implemented a hash table. And you may have noticed something, a downside of hash tables. We had to loop here, right? We had a for loop, looping through the entire memory space in order to find our keys. That was so much easier with arrays. With arrays, we would have had just 3 items and we would have looped over 3 times. Instead, here, we looped over 50 times. Imagine if we had 500. That's even more. How exciting is this? We're starting to learn how things work underneath the hood so that now we have an idea of, maybe if we're using this type of method, objects might not be the best idea. And that's one drawback of objects or hash tables. In JavaScript, we can use something like for in loops to loop over items in an object, which again is very, very slow. And as you might realize, there's no guaranteed order. Every time we're just adding something to our address, but when we grab items from the address, we just go from 0 to 50, even though the items are just randomly placed in different shelves. But I hope now you actually get to see how it works. We're putting items randomly in a shelf, but when we retrieve them, they're all unordered. And that's why coding things out, even though you most likely won't get this asked in an interview, knowing how things work allows you to talk about them intelligently. And I hope this exercise has done that for you. I'll leave this for you to play around with and perhaps add different methods like values that grabs the values instead of the keys. But for now, let's finalize our talk of hash tables by comparing them to arrays. Welcome back. Why hash tables? Hash tables are great when you want quick access to certain values. We remember that searching through an array for an item takes a really long time. We have to loop through every item and see if a certain string or a certain number is in an array. With hash tables, that's really, really fast. And this is why you see hash tables in places like databases, right? We want to search for something in a database and it gives it back to us right away. Similarly, inserting items in a hash table, unlike an array that might shift indexes, is typically O of 1. You just simply have to hash and create the key. Although we have those cases of collision, most of the time that's something that we don't need to worry about too much and we can assume an insert of O of 1. Then there's other aspects that are quite similar between the two. Arrays let you quickly look up the value for a given key. Keys are called indexes in an array, and we don't get to pick them. It's always 0, 1, 2, 3. In hash tables, we can pick them. So hash tables is kind of like a hack on top of an array to let us use flexible keys instead of being stuck with 0, 1, 2, 3. A problem of hash tables that we discussed was the idea of no concept of order. In arrays, each item was placed next to each other on a shelf in memory. Hash tables are kind of placed all over the place. Now that we have an idea of the differences between the two, I think it's time for us to actually work on some exercises and interview questions that will use hash tables in their answers. I'll see you in that one. Bye-bye. Welcome back. It's time for an exciting interview question. And this question comes straight from Google. Given an array, let's say that looks like this, tell me the first recurring character. What does that mean? Well, if we look at this array over here, I want a function that I can enter this array. This input is going to look through all the numbers and tell me which one gets repeated first. So we look at 2, 5, 1, and 2, and we say, 2 has already been seen. 2 is the recurring number. If we look at another example, we see 2, 1, 1, and we stop here because 1 we've already seen before. We can say the first recurring character is 1. If we get an array that has all unique items, we just return undefined. So, how would you go about solving this? Give it a go, see what you come up with. If you need help, perhaps go on Discord and chat with some of the community members, and I'll see you in the solution video. Welcome back. How was it? Did you get it? Was it a tough question? Don't get too disappointed if you weren't able to get the answer. These questions are meant to be tough, to stretch your mind. If they were too simple, then you wouldn't be learning anything. Let's start off with the naive approach. That is, the approach that first comes to mind. For me, the very first one is going to be a nested for loop. Let's have a function. I'm going to call it first recurring character. It's going to receive an input. And because we've already talked about it, I'm not going to do any input validation. We can just assume that we're always going to get some sort of a numbered array. In here, I'm going to loop again. And oh boy, I've done this so many times by now. I hope you're getting sick and tired of just looping through arrays. But hey, now at least we are masters of loops. I plus plus. So in here, in the first loop, we're going to grab the first item in the array. And let's just call this function so we have it here nice and easy and gives us a nice visual. So I'm going to loop through the first item, then the fifth, or the second, the third, the fourth, and keeps going, keeps going. I want to grab this item and then do another loop and check 2 versus 5, 2 versus 1, 2 versus 2, and then say, that's the one. If it doesn't find anything, it's going to go to the next 5 and then compare 5 to 1, 1 to 2, 2 to 3, and so on. So once again, I'm just going to copy and paste this time because we have done a lot of for loops. And simply change the variable to be j. We're going to start at 1 because we don't want to compare 2 to 2. We want to compare 2 to 5 to start off. So we're just skipping a loop, which will help us out. I'm going to say j here and j++. Now, some of you may have been caught here because if we have it the way it is right now and you console log this loop, you'll see that it won't work properly. Because every time this shifts, the outer for loop shifts from, let's say, 0 to next one, the 1 index, j is going to be reset to 1. So 5 is going to get compared to 5, and the function is going to assume, 5 is the recurring character. So a little trick here is to do I plus 1. That is, we always go 1 to the right of where I is, the first index is. So if we're looping, and we're at here, the sub loop, the nested loop, is going to look at I plus 1. So it's going to compare 2 to 3, 2 to 5, 2 to I, because, well, we've already compared 2 to 2, 5 to 1, 5 to 2, 1 to 2 in previous loops. All right, we've done that. In here, we can simply do an if statement saying input I. Does that equal input j? Does 2 equals to 5? Does 2 equal to 1? Does 2 equal to 2? If that equals, then just simply return input I. Otherwise, if we do all this work and nothing happens, we can just return undefined. Let's see if that works. I'm going to run it, and I get 2. Awesome. What if I change this to 1? If I run this, I get 1. Perfect. What if I do just a single item in an array? I get undefined. If I do an empty array, I get undefined. That's good. What if I do 1, 1, or 1, 1? I get 1. That's great. If I do 1, 2, I get undefined. Awesome. This looks to be working. Nice and simple. But as you can see here, we're not being very efficient. We have nested loops, which should trigger, this is O of n squared. And although technically we're actually always looping a little bit more efficient because of I plus I, we're not looping twice over the entire array. In the end, when you remove the constants and simplify things, it's still going to be O of n squared. So how can we solve this using hash tables? Well, let's create a new function we'll call this function by the same name, this time number 2, version 2. It's going to receive an input. And let's change our test case to have the same thing like we did previously. What can we do here? Well, let's use a hash table or an object to do something interesting. That is to add all these as we iterate one by one, so loop through all the items, add them to a hash table, and while we're doing that, we can check to see if the property already exists or the key already exists. We add 2 to the hash table, then 5 to the hash table, then 1 to the hash table, and when we try to add 2, we can trigger a warning saying, we already have 2 as the key. So using that logic, let's see how we can implement it. I'm going to create a map. We'll just call it a hash map for now, because the keys are going to be unique. It's not going to let any duplicate keys. And we can simply do our loops. And in this loop, all we're going to do is say if map, and we can check in this map if it's empty. Now the first check in here, I want to say if the property or if the key already exists, I want to just return the item because we don't need to do any more work. As soon as we find a key that already exists in our hash table, stop all the looping and just return. In this case, we want to return 2. So at index 0, 1, 2, 3, it's going to return and say 2 because, well, this key already exists. So the way we do that in the if check is to simply say if input I, because remember, this is going to equal to 2 when we loop through it. If that exists, then return. Otherwise, we will just add it to our map. So input I is going to equal, and the value can be anything. We'll just leave it at I, which is the index. So 2 is going to equal 0, 5 is going to equal 1, 1 is going to have 2. Let's just console log here to see what is happening. But I want to also return undefined at the end in case none of this happens, in case there is no match. So at the end of the for loop, we'll just console.log map and see what we have. I'm going to run, and I get 5. And there's no log. What just happened here? Well, if we console log up here instead, and take a look at what this is giving us, and run, I get undefined, undefined, undefined 0, undefined 1. What does that mean? Well, remember, we're looping through here, and we're saying, hey, does 2 exist? Does input 0, which is 2, exist as a key? So it's simply saying map.2. Does it exist? And because that doesn't exist, we get undefined. And it's going to go to next. Hey, does 5 exist? No, it doesn't. Hey, does 1 exist? No, it doesn't. Hey, does 2 exist? And as soon as it checks 2 again, map 2, it's going to say, I already have it. It's at index of 0. So this is working. However, because when this gets to 0, the way JavaScript works, it puts 0 here, but in an if statement, 0 is what we call falsy in JavaScript. And that has to do with type coercion in JavaScript, something that a lot of people get annoyed about with the language. So what we would need to do is to make sure that we specify that we want this to not equal undefined. So as soon as it doesn't equal undefined, I want you to return this item. Now, if we run this, we get 2, which is great. If we console.log the map and run this, and let's add it at the bottom here so we see the actual iteration that's happening, we see that it adds 2 at index of 0, then 2 at index of 0, and 5 index of 1, so on and so forth until it stops after the third loop because it encounters 2 again. It's going to check and say, ooh, 2 already exists, just return it. How cool is that? We just made this entire thing with just one loop that is way faster than our first version using hash tables. How cool is that? For me, doing things like this and seeing the power of how learning about Big O and hash tables has improved our coding ability just gets me really, really excited. And I hope this gets you excited as well. We made this function have a time complexity of O of n. We've improved it with one downside. We've increased the memory, the space complexity by O of n because we're creating a new object in this function that needs to keep track of all the items in the array. And in the worst case, when there is no match, it's going to go through the entire item list of the array and hold that information in the map. So we're also going to have, unlike this version where we didn't create any space complexity, we just had space complexity of O of 1, we now have a little bit more. But in turn, we have a faster function. Very, very cool. Now to finish off, I want to give you one last challenge. You see, looking at these two implementations, what happens if we have something like this? What do you think the first recurring character is? If I run this, I get 5 because, well, 5 occurs sooner than 2 because of the way we implemented the second function. However, if I go to the first version of our function and run this, I get 2. Why is that? Well, if we go to the very first part of our function, we see that the way we are doing things is we are going one by one in a different way. We're saying grab 2 and then compare 2 with 5, then 5, then 2, then 3, then 5, then 1, and 2, 4. And then move over to 5, then 5, and 5, and 2. And so on and so forth. And because of the way we have that implemented, it's going to detect 2 and 2 because the outer loop has an index of 0 and has 2 as it's going through the loop before it compares 5 with 5. Versus our second version with a hash table where we had all these items and we were able to compare them once we grabbed all of them. And that's another powerful thing when you think about arrays and hash tables and how you're able to compare things. And based on what the interviewer asked, you might have a wrong answer. Maybe they want you to detect 5 and 5 before you detect 2 and 2. So my bonus question to you, if you have time and a bit of a challenge, is to convert this function, if you want, into something that matches the answer to this, that is to detect 5 and 5. How would you go about doing that? You're most likely going to have to do something interesting here. So good luck with that. Talk to other people on Discord in our community and see if you can figure it out. And I'll post some creative solutions to that problem as students submit them to see how other people have implemented this. But for now, I think we deserve a break. I'll see you in the next one. Bye-bye. Another data structure down, hash tables. By now, you should absolutely love them because, well, they're very useful. They're used everywhere. And the funny thing is that it's probably the most common interview question where you use a hash table to optimize something, kind of like we saw in our interview question. By using hash tables, we optimize those nested loops that are O(n) squared to O of n, linear time. This is a question that comes up again and again that I promise you, if you notice this pattern, it will be extremely useful for you in an interview. And undoubtedly, you'll have an instance where you have to use it and follow this exact same step. In this section, we learned that hash tables have really fast lookups, but remember, we need a good collision resolution needed. Usually, we don't need to worry about this because our language and computer underneath the hood take care of that for us. It allows us to do fast inserts, and depending on the type of hash tables, such as maps in JavaScript, we can have flexible keys instead of an array that has 0, 1, 2, 3, just numbered indexes. The downside with hash tables is that it is unordered. It's hard to really go through everything in order, and also it has slow key iteration. That is, if I want to grab all the keys from a hash table, I'll have to go through the entire memory space as we saw when we built our own hash table. Looking at the Big O cheat sheet, we can see that hash tables has a search, insertion, deletion of O of 1, but in worst case, due to collision, there are some O of n operations that could happen. And if we go to our mind map, we can now cross off hash tables off our list. We understand the Big O complexity. We also understand that with collisions, we might want to use something like linked lists, which we'll talk about very shortly. In our exercise, we just simply used arrays. We also learned the idea that hash tables in interviews are usually useful for improving time complexity, especially of nested loops. The trade-off being that we can have fast access, but more memory. Going back to our question that we had a few lessons ago, where we had to find the common item of two arrays. We had array 1 and array 2, and we had to see if any of these arrays contained similar items. We had one that didn't, and the second version, where x and x, both arrays contained x, it would return true. Our first iteration of that exercise, we had to use two for loops that were nested. So that created A times B complexity. However, using hash maps, we were able to just do one for loop and optimize this function. Like I said before, this is such a common pattern that we'll be talking about it later on in the course as well when we talk about dynamic programming. If we go back to our cheat sheet that I shared with you at the beginning of this course, we can now cross off a few things off the list that we haven't talked about in the good code checklist. We talked about the good use of data structures, when to use hash tables over perhaps arrays. The idea of code reuse and not repeating yourself is something we've been following and should be familiar to all of us. We also talked about modular code and making code more readable, which allows code to be more maintainable and testable. We talked about how usually in an interview, we want to avoid the O n squared operations, and we saw that we're able to do that with hash tables. But we did see that with a hash table, we had to increase our space complexity to O of n because we created this new variable that keeps track of all the items in the array. So that is the trade-off. And then we can cross off a few heuristics. For those who don't know, heuristics are kind of like rules or simple tricks that are going to come up over and over and over that you can use in an interview. Hash maps or hash tables are usually the answer to improve time complexity. Again, hash tables are some of the best way to optimize your code. And looking at time versus space trade-off, sometimes storing extra state in memory, like we did with hash tables, can help the time or the runtime. And then finally, space-time trade-offs. Hash tables usually solve this a lot of the time. You use more space, but you can get a time optimization to the process. I know we've only talked about two data structures, but I think these two are the most important. Moving forward, we're going to use them to learn about others. Good job getting this far. Take a nice little break, have some coffee, and I'll see you in the next video. Bye-bye.